Okay, so I'm using Universe Sandbox, which is a gravity simulator. And I'm going to put an Earth in the middle of space, and I'm going to shoot about 7 different asteroids towards Earth. And each asteroid will have a slightly different trajectory, and my goal is to get a trajectory such that it will pass Earth, but whip around it, come back to the other side. And this is all happening because of the gravitational force that Earth is exerting on the asteroid, but the asteroid is also exerting a force on it. So I'm using conservation of linear momentum as well as conservation of energy to predict the speed of the asteroid as it comes back on the other side. So if I know the velocity of the asteroid as it approaches Earth, I know Earth's velocity and the masses of each, I can compute the velocity of the asteroid as it comes back on the other side. So this is an example of what we're seeing in the Martian movie, where the Hermes approaches Earth, trajectory set so it'll come back on the other side, and we're going to compute what that velocity is. So here, of the 7 trajectories of asteroids, looks like 2 came back perfectly on the other side. Okay, so here's a collision between 2 masses. Mass 1 moving this way with velocity v1 initial, mass 2 moving this way with velocity 2 initial. We can use conservation of energy and conservation of linear momentum to derive these 2 equations. So I can get the velocity of this ball after the collision. If I just know this information, I can get the velocity of this ball after the collision knowing this information. Now I'm going to use these equations to model the interaction between Hermes and Earth to prove that gravitational assist really does work, and you can add tremendous velocity to the spacecraft after it interacts with a much larger mass. Again, Hermes interacting with Earth. But before I do that, I want to show you how this applies to collisions of balls. And the collisions of balls is perfectly analogous to the interaction of Earth and Hermes via the gravitational force. So 2 balls colliding, one much larger than the other, is analogous to the Hermes interacting with Earth, which can also be modeled mathematically as a collision. This mass has a velocity of 1 meter per second. Okay, to the right, this mass, which is quite a bit larger, has a mass of 0.5 meters per second to the left. The total kinetic energy is 0.43 joules. The combined momentum is minus 1.4. Okay, so let's take a look at this collision and look at the numbers after the collision. Okay, so this mass increased in speed to 1.9 meter per second. The larger mass dropped a little bit in velocity, slightly, from 0.5 to 0.4. The total linear momentum is conserved, still at minus 1.4, and the total kinetic energy is also conserved of the system. It's still 0.43 joules. And like I said before, it's analogous to Hermes interacting with Earth, as the velocity of Hermes after the interaction with Earth was much greater than it was before the interaction with Earth. Okay, so here's the mathematics of the collision you just saw. Had a 0.1 kilogram mass here, 3 kilogram mass here, and this one was moving at 1 meter per second to the right, so plus. This was moving at 0.5 meters per second to the left, so minus. And I'm going to use this equation to figure out the velocity of this ball after the collision. So m1 minus m2 is 0.1 minus 3 divided by the sum of the masses, which is 3.1, times velocity of this before the collision, which is 1, plus 2 times mass 2, which is 3.0, divided by the sum of the masses, 3.1, times velocity of this ball before the collision, minus 0.5, and that gets me minus 1.9 meters per second, which was the velocity of the smaller ball after the collision. So as you see, once again, its velocity almost doubled. The velocity of the larger ball is 2 times mass 1 divided by the sum of the masses times the velocity of this ball before the collision plus the difference between the masses divided by the sum of the masses times the velocity of this ball before the collision is minus 0.5, and this sums to minus 0.40. So the larger ball slowed just a bit. And the same is true when Hermes interacted with Earth. Hermes increased its velocity dramatically, tripled it, whereas Earth's velocity dropped, but it drops by so little you probably couldn't even measure it. Okay, so let's apply this mathematics to the Hermes approaching Earth and slingshotting around Earth. Here are the assumptions. The mass of Earth is 6 times 10 to the 24th kilograms. Let's say the mass of the Hermes spacecraft is 100,000 kilograms. The velocity of the Hermes spacecraft is 15,000 meters per second, moving in the positive x direction. The velocity of Earth is minus 30,000 meters per second, moving in the minus direction. Okay, so I want to know the velocity one final. Okay, so I want to know the velocities of the Hermes after the collision. So I'm going to use this equation. So mass 1 is the Hermes, so 100,000 minus the mass 2, which is Earth, 6 times 10 to the 24th, divided by the sum of the masses, 100,000 plus 6 times 10 to the 24th, times velocity of the Hermes initial. It's moving to the right, so times plus 15,000. I'm going to add to that this part, so 2 times the mass of Earth here, divided by the sum of the masses, times velocity of Earth. And I've got going in the negative direction, so 30,000. So work this out. It's going to come out to be a minus number. Work this out and add them together, and you get minus 45,000 meters per second. So the Hermes spacecraft went from 15,000 meters per second as it approached Earth to 45,000 meters per second as it slingshot around Earth. So the movie The Martian has that correct, that this trajectory is set appropriately. You could get a gravity assist as it slingshots around Earth.